All right, this is induction video number 2, and what I want to do here is address the way electromagnetic induction can be connected to energy and conservation of energy and work. And the reason I'm giving this its own dedicated video is that it's a really common AP exam question to have some kind of an induction event going on, and they ask you, like, how much work is required to do blah, 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 or what is the rate at which energy is consumed by this system, blah, blah, blah. A lot of the time, this involves, like, a metal bar that's, like, falling through a magnetic field. So, like, if you let go of it and gravity pulls it down, falls through a magnetic field and a bunch of induction stuff occurs, and I don't know, they really like these questions. So I've started with one of the same diagrams I had in the previous video about where did my scratch work get to? This is one of the diagrams from my previous video about a wire loop that's being pulled out of a magnetic field. The magnetic field points into the screen. And when the magnetic field points into the screen and you pull the loop out of the field, you're going to get, in this case, a clockwise induced current. You can figure out that it's clockwise based on either Lenz's law and a bunch of flux stuff, or by just thinking about if you pretend there's a little positively charged particle in this wire, and the particle is moved to the right, which way is the magnetic force? Magnetic force is going to be up. And so that gives you a clockwise current in the loop. I've labeled a couple of other things. I'm going to say that the edge length for the loop is called L. I drew it as a square. It could be a rectangle. And then it's just the vertical length, which is L. And I've also named X to be this distance here. So that's not the entire edge length on the bottom, it's just the amount that's inside the magnetic field. So the first question that I've asked myself here is, what's the EMF? In my previous video, I didn't actually calculate any EMFs. I just talked about how to use the conceptual ideas to figure out the direction of the EMF, but I didn't actually calculate one. So here, let's calculate one. Like, it's going to be an expression. There's no numbers, but I can still calculate it. I know that the EMF should be, let's just worry about the magnitude, should be n times d phi dt. That's what Faraday's law says. Let's let n equal 1, just so we don't have to worry about that. So basically, the EMF is d phi dt. Well, what is phi? Phi is supposed to be the magnetic field times the area. It's a dot product, but everything is like perpendicular here, so the dot product is, optimized. So it's just B times A. I'll even take that dot out of there so you don't get distracted by it. But the thing to keep in mind here is that the area A represents only the area where there's actually field. So for the instant drawn in my picture, the area is L times X. It's not L squared, even though the loop itself is a square with area L squared. The magnetic field only exists in this part of it, and so the flux is based only on that area A. So it's d by dt with B L X. B is constant with respect to time, and L is also constant with respect to time. But X isn't, because X represents the amount of the loop that is inside the field. So what is d by dt of that x? That would be the velocity v. So the EMF is going to be equal to BLV. Now, this result, just as a side note, this result is something that we already saw when we were talking about the Hall effect. If you have a conductor moving through a magnetic field, the magnetic forces on the charged particles inside the conductor produce a potential difference that polarizes the conductor. And so you generate like a potential difference or a voltage between the two edges of the conductor. If that conductor is part of a complete circuit like this, then that potential difference causes the current to flow. And that's why this is an EMF. So we already saw this exact same result before. This is also called motional EMF, because it's an EMF that comes from motion. So that's something that you're likely to see on the exam. But that's my result, BLV. All right, next question. Oh, I guess when I wrote this out before, I guess I left it as just n. So if n isn't 1, then you just need to have the n still there. All right, next question. How much force is felt by the left edge of the loop? I'm talking about magnetic force here. What? Magnetic force. Now, before I get into that, you may be wondering, why don't I ask about the other edges? Well, the right edge, there's no magnetic force there because there's no field. On the top edge, there is going to be a magnetic force. I have current moving to the right through a magnetic field. And if you go through your right-hand rule for that, with the current going to the right and the magnetic field into the screen, you're going to find that there's a force pointing up on that edge. But you will also find that there is a matching force pointing down on the bottom edge. They're opposite in direction, and they're going to have the same magnitude because the current is the same in both places, and they have the same length. Both of them have length x. So those two forces cancel each other out, and they don't really have any effect on the energy or the motion of the system. However, on the left edge, there is current flowing up through a magnetic field, and that's going to make a force which, like the other two forces, points outward, but outward on this side is to the left. So there's going to be a force to the left. And I want to get an expression for it. Well, force on a current carrying wire is IL cross B. The cross product here is optimal, so I don't need to really worry about it because everything's at right angles. So it's just going to be ILB. Although I wrote the letter I in the diagram, I want to break it down a little bit. Current is going to be the EMF divided by whatever the resistance of the loop is. It's a piece of wire. A lot of the time we just pretend the wires have no resistance, but they have some, at least a little bit. And so using the equation that is not actually Ohm's law, by using the definition of resistance, I can say the current has to be E over R. And then I also have the L and I have the B. But the reason I wanted to make that swap is because I have an expression for the EMF already. So I'm going to take the EMF expression and stick it into here. Notice that there's a B and an L already. So I'm going to have N b squared L squared v over r. And, oh, I need an n. I need another n. I'm going to stick the other n initially way back here. Why do I need another n? I need another n because if this circuit actually has, like, 100 versions of the wire all looped around, that means the force is going to be 100 times stronger because there's actually 100 wires all going up on the left edge. Each one of them feels the force. So I need to carry that n through. That makes the n also squared. Yeah. Okay. So that's my expression for the force on the left edge of the wire. And again, that is going to be the same as the total magnetic force on the loop, because the other edges are either 0 or they cancel each other out. So if the loop, say, had some initial velocity v, I know that instantaneously speaking, there's going to be a magnetic force with this magnitude acting to the left. If there are no other forces of any kind, that means that the loop is going to be slowing down. It's going to be moving to the right, but there's a force to the left, which would slow it down, so it'll gradually come to a stop. This is connected to the idea that I stated in another video, that the direction of the induction, the direction of the induced current, always ends up going in a direction that's going to, like, counteract the thing that's causing it in the first place. So the reason that there's induction in the first place here is that the loop is moving to the right. So what the net result of the induction is going to be is to try to stop that motion. So there's a magnetic force that tries to, like, put on the brakes, slow down the motion, bring the loop to a stop. If we're going to say that the loop continues to move to the right at a constant v, that means that there has to be some other force also being exerted. So, like, I must be holding on to it and pulling on it. There's resistance, not just like Ohm's resistance, but like I yank on it, I try to pull it out, and I can feel something pulling back against me. There's nothing else touching it. It's strictly an electromagnetic effect. But when I try to yank the coil out, I can feel this magnetic force working against me. So if I want to keep that velocity constant, I have to also pull. I have to continue to pull, and I have to pull at this exact speed, or force. I'd have to pull with that much force. That's the strength of the magnetic force. I want the net force to be 0. So that means I have to pull at that strength. So one of our power expressions when it came to mechanics was force times velocity. That tells you the power being delivered to an object by the force F. So I know that the force F which I exert has to be NLB quantity squared times V over R. And so the power is that force times V. So the power that I deliver to the wire loop is NLBV squared over R. And then the last thing that I want to show you is that that power is the exact same amount of power that you would get from an electricity calculation. I already said that the loop has a resistance R. I can calculate the electrical power, power dissipated by the resistance, by doing I squared R. I is this expression from earlier. The resistance is called R. And so I squared R ends up giving me the exact same power expression. So these two things have been calculated in completely different ways. One of them is a mechanical energy, the other one's an electrical energy, or power. I should be saying power here because they're rates. But even though they're completely different from each other, got completely different methods, got the same result. And that is because the law of conservation of energy. So like none of this stuff is free. The energy that's involved with making a current flow during an induction event, it comes from somewhere. It usually comes from some mechanical action, which is pulling a wire loop or causing something to spin or whatever. There's some other cause. Something is providing energy, which induces a change, which changes a flux, which makes the EMF, which causes a current to flow. But all of these things are connected to each other, and the amount of energy involved is going to be consistent through all of those steps. So again, this is an idea that comes up very frequently on the AP exams, where you'll have to do some sort of manipulations like this. And the problems from me, you're going to see a bunch of the same kind of stuff so that you get to practice with it yourself. But it's a very safe bet that you'll see something like this on the exam as well.